In 1942, the United States government had unlimited money, the best engineers from MIT, and one impossible problem. They needed to build a machine more accurate than any machine that existed. Not close, not almost. They needed tolerances of 1/10,000th of an inch for the Manhattan Project, where the width of a human hair meant catastrophic failure. The solution wasn't a supercomputer, wasn't a secret alloy, wasn't some revolutionary technology. It was a guy with a wooden stick and a sharp piece of metal, scraping surfaces by hand for 10,000 hours. This is the story of the scrapers, the men who built the most precise lathes in American history using nothing but muscle memory, Prussian blue paste, and obsessive repetition. Why those machines from 1943 are still more accurate than most modern CNCs, and why, in 2026, if you can find one of these men, they're making six-figure salaries. Because there's a limit to what machines can do alone. And 80 years later, we're just starting to remember that. Let's start with a question that sounds like philosophy but isn't. How do you build a machine more accurate than the machine that made it? This isn't abstract. It's a fundamental physical limit called the mother machine principle. If your milling machine has tolerance of plus or minus 0.001 inches, every part it makes will be plus or minus 0.01 inches or worse. Error doesn't disappear. It accumulates. Setup, fixturing, tool deflection, temperature, everything adds error. So if you want to build a machine with tolerance of plus or minus 0.0001 inches, 1/10,000th, you need a mother machine capable of plus or minus 0.0005 inches or better. But in 1942, that machine didn't exist. So when the War Department handed the Monarch Machine Tool Company of Cincinnati, Ohio, an essentially unlimited budget to create the most advanced precision lathe in the world, they hit a wall. Their state-of-the-art grinding machines, purchased at enormous cost, weren't accurate enough, and neither were anyone else's. The engineers did something that today would be considered industrial heresy. They admitted their machines couldn't do the job. And they called in the scrapers. Now let's clear something up immediately. Scraping, hand scraping of metal, is not a lost secret. It's not a mystical art transmitted by ancient craftsmen in hidden workshops. It's a documented technique, taught in books like Foundations of Mechanical Accuracy, published by the Moore Special Tool Company, and the classic Machine Tool Reconditioning by Edward F. Connolly. The secret isn't the technique. The secret is that almost nobody wants to learn it anymore. Because it takes 5 to 10 years to master, pays nothing while you're learning, and requires something modern manufacturing culture rejects: repetitive manual work with no instant results. But in the 1940s, companies like Moore Special Tool in Bridgeport, Connecticut employed more than 20 full-time scrapers. Men who spent 8 hours a day, 5 days a week, scraping metal surfaces to tolerances that no machine could match. Today, in the entire United States, there are maybe fewer than 100 active scrapers with that level of skill. And we're about to find out why that matters. The tool looks primitive. A wooden handle, usually maple or oak, with a tungsten carbide blade fixed to the tip. The blade is sharpened at a specific angle, typically 30 to 40 degrees. That's it. No motor. No electronics. No computer control. The scraper pushes this blade across a cast iron or steel surface with controlled force, removing metal shavings of 0.001 to 0.0005 inches per pass. That's thinner than a sheet of paper. Removed by feel. Here's how the process actually works. Step 1. You have a reference plate, usually fine-grained black granite, dimensionally stable, doesn't expand with temperature. This plate has been lapped to tolerance of plus or minus 0.00002 inches across its entire surface. Step 2. You apply an extremely thin layer of Prussian blue, a contrast paste, to the reference plate. Step 3. You place the metal surface that needs to be scraped onto the plate. Apply uniform pressure and slide the piece in a circular motion. When you lift the piece, the high spots, the areas that actually made contact with the reference plate, are marked with blue. Step 4. You scrape those high spots. Only those spots, nothing else. Step 5. Repeat. Hundreds of times. Thousands of times. An experienced scraper can see the curvature of a surface just from the distribution of blue spots. He knows from instinct trained over decades how much metal to remove, at what angle, with how much force. There's no measuring instrument involved at this stage, no micrometer, no digital indicator. It's visual feedback, calibrated muscle force, and obsessive repetition. In the 1940s, this is how they built the machines that built the atomic bomb. And if you think that sounds inefficient, consider this. Those machines are still in tolerance today, 80 years later. But now we hit another problem. How do you know your reference plate, that granite or iron surface you're using to mark high spots, is actually flat? If your reference is convex or concave by even 0.001 inches, you transfer that error to every piece you scrape. You've created an error propagation system that makes everything worse. The solution is one of the most elegant pieces of geometric proof and precision engineering. It's called the three-plate method, documented by Wayne Moore, and it's brilliant in its simplicity. You start with 3 cast iron plates of identical size. Call them A, B, and C. They don't need to be perfect. They can be warped, wavy, with error of 0.01 inches or more. Doesn't matter. Step 1. Scrape plate A against plate B using Prussian blue to mark high spots. Level both until they match perfectly. At this point, you have 2 surfaces that coincide, but not necessarily flat. They could both be concave or both convex, mirrors of each other. Step 2. Scrape plate B against plate C, again, until they match. Step 3. Here's the trick. Scrape plate C against plate A. What happens mathematically, and this has been geometrically proven, is that the only way 3 surfaces can match perfectly when scraped in rotation is if all 3 are absolute flats. If A is concave and B is convex to match it, when you introduce C and try to make it match both, the geometry fails. You cannot close the triangle without flatness. It's impossible. With 3 cast iron plates, a scraper, Prussian blue, and enough time, you can achieve flatness of plus or minus 0.00002 inches, 20 millionths of an inch. Without a single electronic measuring instrument, the Moore Special Tool Company used this process to create master plates that served as reference for all the jig borers they manufactured between 1924 and the 1980s. Many of those plates still exist, still in use, still within original tolerance. 70 years later, compare that to a modern linear guide on a production CNC machine. Estimated service life under heavy use, 4 to 8 years. So here's the obvious question. If modern CNC grinders can achieve tolerances of plus or minus 0.001 inches, why would anyone still use hand scraping? The answer is in 4 fundamental differences that don't appear on any specification sheet. Difference number 1, heat. A grinder uses an abrasive wheel spinning between 4,000 and 6,000 RPM, removing metal through friction. This generates intense heat, easily 300 to 500 degrees Fahrenheit in the contact zone. Even with flood coolant, you introduce thermal stresses into the metal. The material expands during operation and contracts when it cools. This creates internal microcracks and distortions that take years to fully manifest. Scraping is a cold process. Temperature in the cutting zone rarely exceeds 100 degrees Fahrenheit. No thermal stresses. No post-process distortion. Difference number 2, clamping forces. To grind a surface, you must clamp the part with vices or fixturing devices. This introduces mechanical force, typically hundreds of pounds of pressure, that slightly distorts the geometry during operation. When you remove the clamps after grinding, The part relaxes and recovers some of the distortion. Result: the surface isn't as flat as the in-process measurement indicated. In hand scraping, the part isn't clamped. It rests freely on the reference plate, supported only by its own weight. No external forces. No induced distortion. Difference number 3. Surface texture. A ground surface is smooth, almost like glass. Under a microscope, you see uniform texture with directional scratches left by the wheel. That smoothness has a problem. It expels oil. When you place two perfectly smooth surfaces in contact under load, like a carriage sliding on a lathe bedway, the oil film is gradually expelled by pressure. What remains is metal-on-metal contact at microscopic scale. This causes the phenomenon called stick slip, the jerky motion you feel when you try to manually move the carriage of an old, poorly maintained lathe. When a scraper works a surface, he doesn't leave it smooth. He creates a deliberate pattern of marks, usually a crosshatch pattern called flaking, with density of 20 to 30 points per square inch. Each of those marks is a microdepression, a pocket that retains oil. Under load, the oil film is maintained in these reservoirs, ensuring constant lubrication and metal-to-metal separation. It's counterintuitive. A technically rougher surface performs better over time than a perfectly smooth surface. Difference number 4. Geometric longevity. Here's the data that matters. Ground surfaces on industrial production machines, under heavy use 3 shifts, 5 days a week, typically lose their tolerance class in 4 to 8 years. Hand-scraped surfaces on machines of the same class maintain geometric precision for 20 to 50 years under the same conditions. The Monarch 10EE that was manufactured in 1943, used continuously in a military tool room until the 1990s, now belongs to a collector in Ohio. Recent measurements with laser interferometer show the bedways are still within plus or minus 0.002 inches along their entire length, 80 years. Now let's talk about what happened to this industry. Between 1975 and 1995, the American machine tool industry entered structural collapse. Companies like Cincinnati Millicron, Giddings & Lewis, and Monarch Machine Tool itself either went bankrupt or were sold to foreign conglomerates. The Moore Special Tool Company closed its doors in 1990. The reasons are well documented. Japanese competition, CNC automation, the shift to recirculating ball linear guides, faster to manufacture, accurate enough for 99% of applications, and much cheaper. You could buy a CNC milling machine with linear guides for $80,000. An equivalent machine with hand-scraped bedways would cost $250,000 and take 6 months longer to deliver. The decision was obvious for most buyers. And with the decline of the machines came the decline of the scrapers. In 2010, the average age of a qualified scraper in the United States was 63 years old. There were no apprenticeship programs, no university courses. Technical schools had eliminated scraping from their curricula decades before. It was considered obsolete, a waste of instructional time. Then something unexpected happened. Around 2005, manufacturers of ultra-precision machines, especially in aerospace and optical lens molds, began noticing a problem. Their state-of-the-art CNC machines with linear guides and active thermal control couldn't maintain stability in finishing operations with tolerances of plus or minus 0.00005 inches. 50 million. The reason: dynamic rigidity. Recirculating ball linear guides have extremely low friction, which is great for rapid traverse speed. But they also have reduced rigidity under variable cutting load. When you're making a heavy roughing cut and suddenly transition to a light finishing pass, the machine floats microscopically on the balls. This introduces high-frequency vibration, chatter, which ruins surface finish. Scraped bedways, on the other hand, have controlled friction and viscous damping from the oil film. They absorb vibrations. They're rigid under variable load. Elite Japanese manufacturers Matsuura, Sadek, Yasta never completely abandoned hand scraping. They reserved it for their top-of-the-line machines, intended for customers willing to pay $500,000 to $2 million for a single machine. American companies like Haas Automation and additive manufacturing startups realized their products couldn't compete in ultra-precision applications. They looked at what the Japanese were doing, and they realized the Japanese had preserved the skill. Today, in 2026, a qualified scraper in the United States can command salary of $100,000 to $150,000 a year. Some companies, especially in California and Massachusetts, where semiconductor and optical equipment manufacturers are concentrated, offer $180,000 plus benefits. And still, they can't hire because you can't train a scraper in 6 months. You can't watch a YouTube video and learn it. You need mentorship, time, and something modern manufacturing culture rejects: repetitive manual work that doesn't produce immediate results. A scraper apprentice spends the first 2 years just learning to hold the tool correctly, learning to read the Prussian blue pattern, learning how much metal was removed by the sound the tool makes when cutting. No gamification, no digital interface, no instant gratification. It's sensory feedback, muscle, and patience. So what's the actual secret behind the world's best lathes? It's not an exotic material, not a special alloy developed in a secret government lab. The secret is that there's a limit to what machines can do alone. You can automate production, you can speed up the process, you can reduce costs, but you can't yet automate the tactile perception of a scraper who feels the geometry of the surface through the tool. You can't replicate the human judgment of when to stop scraping a high spot, and you certainly can't replicate the patience required to scrape the same surface 1,000 times until the Prussian blue spots are distributed with uniform density of 25 points per square inch. The Monarch 10EE, that machine from 1943 that still operates at factory tolerance, isn't a miracle. It's not magic. It's the result of tens of thousands of hours of specialized manual labor, applied with obsessive precision by men whose names never appeared in any Manhattan Project report. Some of them signed their work. A small metal plate attached to the side of the bedway. Hand scraped by, followed by a name and a date. It was a signature of warranty. A statement that this machine was built right, that it would last decades, that it wouldn't fail when you needed it. Today, you don't find those plates. Machines are manufactured by robots, tested by software, delivered with a 2-year warranty and a technical support number. And for 99% of applications, that's enough. But if you need a machine that will operate for 30 years, that will maintain tolerance of plus or minus 0.001 inches even after millions of cycles, that will absorb vibration, maintain rigidity under variable load, and never exhibit stick slip, you need a scraper. And those men still exist. They still work, still teach when they find someone willing to learn. But they're aging. And with each passing year, there are fewer of them. The secret behind the world's best lathes isn't a secret at all. It's a choice. The choice to value durability over speed, precision over convenience, human skill over automation at any cost. And as a society, we stopped making that choice about 40 years ago. Maybe it's time to ask, what else did we lose when we decided that good enough was good enough?